Thank you very much, Ben. As you can see from the topics that I'm discussing, it's heterogeneous, very relevant to this particular workshop. So what I like to do is discuss some of these heterogeneous problems, and I'm only going to concentrate using deep neural network to solve some of these problems. So as you can see from the list, there are several topics. For example, Sean talked about cross-spectral face recognition. There is a sketch versus face photo and several other ones. Because of the lack of the time of the weather change, I'm only going to talk about a couple of them rather than talk to with regard to all of them. So let me quickly talk about what are the problems in heterogeneous face recognition. Of course, there are other modalities, but for this topic, we're only going to consider faces. So as Sean discussed, one of the problems is that you're given a thermal imagery as a probe. You want to match it against your gallery of visible imagery. Now, the face could be any different spectral range. One of the major problems is in the thermal region. In the thermal region, as you can see, a lot of information about the face, such as the surface topography of the face, is basically washed away. The details has disappeared. So it becomes very difficult to match such a face with its corresponding original image in a gallery. And that's the major problem that we're trying to solve. How to relate the thermal information and relate it to the visible information. This relationship is not linear, and that's what makes it difficult to solve. Now, because in the thermal imagery, the details about the face is washed away, more recently at ARL, Army Research Lab, we have been investigating the polarimetric information about the light in the thermal domain. The polarimetric state information of the light provides you some surface topography. And the goal is now, given the thermal image and its polarimetric information, can you basically match these set of images with corresponding visible imagery? And we will show you some result that we can do that, and performance goes higher than its corresponding thermal. Another major problem is, again, heterogeneous problem. Given a sketch of somebody, can you match it, of a suspect, can you match it against a gallery of visible imagery? As you can see, the sketch, it's quite different from the actual photo. So how do we do that? Again, the relationship is not quite linear. There's a lot of nonlinear process can be exploited to match those two modalities. So I will show you also some results on that, how to match sketch versus visible imagery. Another problem is cross-age matching. Of course, this is not heterogeneous. We're still working on homogeneous modality. Given somebody at 5 years old, can you recognize this individual at older age, 10 years old, and so on? This is very important for Homeland Security because children are basically adopted or they are missing and they appear in 10 years, 15 years. We want to know, is this person the same person as in 10 years from now? Also, children passport, they're not only valid for 5 years, but children at very young age very quickly, the face does not match. Can we develop algorithms to match across the ages? Now, if you are into face recognition, one of the major problems, again for law enforcement, is how do you discriminate or distinguish between two identical twins? At West Virginia University, we have been collecting a lot of data for FBI, and the goal is, can your face recognition algorithm distinguish between two identical twins? All these pictures are identical twins at different years. And we have several years of these twins that we have collected data. Now imagine your face recognition algorithm should be extremely good to distinguish between two identical twins. If you can do that, then obviously you can distinguish between different people. So that's a good test for even image face recognition algorithms that companies develop. Similar problem exists, for example, in lookalikes. How can we distinguish between lookalikes and so on? Also, cosmetic surgery. For example, the passport is valid for 10 years, and if you go through some cosmetic changes and you go through the exit entry, and then question is this face in the passport the same person that carrying it? So that's extremely important for Homeland Security and so on. Also for makeup, if you do extreme makeup, again the same thing, it wouldn't match your passport or your driving license. So can we basically develop algorithms to do this cross match between different makeups? So let me go back into our heterogeneous problem. So basically, remember we have a face and it's being imaged in different wavelengths, in the visible and in the thermal imagery. And our goal is to basically see if we can match this thermal with our visible imagery. What people have done previously, and what they have done is they extract features from the thermal, such as HAWK, SIF, the classical computer vision features, and try to match those features with the features extracted from the visible imagery. Now, these feature extractions are extremely powerful because they're being developed by humans, but one of the major questions that these days arise in computer vision is, what does these features have to do with the imaging characteristics of the data? Because you're extracting the HAWKs and the SIFT from thermal, and you're extracting the same features from the visible. These features have nothing to do with actually the process of imaging of the data. So we call these days, we call this in computer vision, the handcrafted features. And we are moving from these handcrafted features towards some data-driven feature extraction. In a minute, I will show you that what we're going to do is we're going to extract features using deep learning or the old neural networks, and we're extracting dedicated features for each one of these modalities. So the features are dedicated for modalities, and what that makes it interesting is that they are not hand-picked or handcrafted features. Now, there's a lot of buzzwords and heaps about deep learning, but deep learning is nothing new. It's been around for a long time. So if you look at the history of deep learning, obviously single neurons, the model of single neurons started in the 1940s. And gradually, Professor Rosenblatt from Cornell University in 1950s basically put some of these neurons together and called them perceptrons. So they were using these perceptrons implementing very simple things. And later on, with Drew and Hoof, Stanford University, basically they're using for adaptive filtering for in communication. So the field is not new, has been around for a while. Now, one of the problems was people were basically putting the layers later on, and that was in late 1960s, early 70s. One of the major problems was they didn't know how to basically train these multi-layer perceptrons, MLP. Until 1974-76, people were able now to training these multi-layer perceptrons, and we were getting very good results. But the major problem those days, in 80s and even in early 90s, that's when I started to do neural network, the problem was we didn't have data, and we didn't have the computational power to be able to implement this. There was lack of data was a major problem. Now, even CNN is not new. What happened is, I believe in 1980s, neurocognitron is actually the beginning of what we call now CNN, was by Professor Fujikama in Tokyo University. And basically, he started to put things like convolutional neural network using kernels and so on. He didn't call it convolutional neural network, he called it neurocognitron. Then Lucan basically picked that up And basically that's how CNN came into play. Even before CNN, there was called time delay neural network in speech processing, which won the best paper in IEEE signal processing. So CNN was around for a while. Unfortunately, because lack of data and the computational power, CNN or deep neural network basically phased out for a while, and SVM basically picked up. So in late 1990s and early 2000s, CNN became very popular, and people in computer vision were exploiting SVM for different applications and so on. Until 2010, 2012, where Google basically started a new project, which called Google Brain Project, and they started to use deep learning, especially for speech processing. And then basically one of the students of Hinton in Toronto University, Alex, basically used nothing more than Lanette, which was done previously. Lanette is only 5 layers. All he did was basically use 8 layers rather than 5 layers. But now what happened was he trained AlexNet over ImageNet database, which is over 1.2 million images. And what happened was he also showed how to use basically 2 GPUs to train these convolutional neural networks. And basically he won the competition, and that's basically the history of deep learning in computer vision. Things picked up and people started to increase the number of layers, and as you can see, the one which also won the ImageNet competition in 2015, ResNet, which is 152 layers of convolutional layer and a couple of fully connected. And basically, deep learning resonated, and basically people are now using deep learning for many applications. Now, going back to our heterogeneous problem, how do I use deep learning to solve this problem? So let me remind you of what the problem is. Basically, you are given a probe, and a thermal probe, and you want to identify this thermal probe from a gallery of visible images. Since we are going to use deep learning, I need some training data. So you are also given a training data, pair of images of different IDs. So for every visible imagery, you have the thermal. We're going to use only the training data to train my deep learning, and then we're going to test it on our probe. Okay, thermal probe. So the technique we are going to use basically is coupled CNNs. So I have 2 CNNs and I coupled them together. Basically the 2 CNNs, one is trained for the visible imagery. So if that's your visible imagery, you basically train it and you will get an output. Basically this is fully connected layer. You get a ZX. Your thermal, same thing, you get a ZY. Now, there is a lot of engineering going on when we do this, okay? It's not enough time to go through it, but we pre-train these on many images before we actually train it on our training data sets, because our training data set is very limited number of pairs we have. So on our training data set, basically we put the visible imagery here and the thermal imagery here, and we force the output of these 2 neural networks to be as close as possible, okay? And we do that with the well-known classical contrastive loss, which forces the 2 networks output to be as similar as possible if the 2 inputs are from the same ID. If the 2 inputs from different ID, we want the difference between ZX and ZY to be as far as possible. So that's where the coupling is done. The coupling is done through basically contrastive loss. Now, as I said before, although we pre-train our neural networks, the CNNs, with lots of other auxiliary data, and then we train them using contrastive loss to couple them with our training data, still there's not enough training data. It actually basically it memorizes things and it doesn't generalize to the test data very well. So one of the things we did was we reduced the number of weights. If you look at the convolutional neural network, most of the weights is in the fully connected layer, not the convolutional layer, because convolutional is obviously shared. That's the advantage of CNN. So what's happened is, rather than having fully connected layers, we don't have any fully connected layers in this diagram. The only difference is this pooling here is now global pooling. Global pooling means that each feature maps you average. So if at the last convolutional layer, if you have 512 feature maps, basically you have 512 values when you do global pooling. That means every feature map you just average. So you get 512 values out here and 512 values out in the thermal CNN. And what you do is basically you apply contrastive loss to minimize, to adjust the weights of the two networks, and that's where the coupling is going on, in order basically to make the ZX and ZY to be equal for all your training data. So hopefully everybody knows what is contrastive loss. It's well known in neural networks. It's nothing new. Again, it's the first paper was in 1986, 1987. And then again, it has been picked up for different applications and basically is used for Siamese networks. And we have used that Siamese also for many other applications. But basically the goal of coupling here is when basically you show a pair of images, one thermal, one visible imagery, and you force, when they are same ID, you force the output of the neural networks, to be the same, or as close as possible. And if you're from different IDs, we call that imposter pairs, what you do is you force the output ZX and ZY to be different. Okay, that's the goal, right? So basically that's what the contrastive loss does for us, and it works extremely well. And if you look at the result for fully connected layer, that means I only have one fully connected here, okay? And then what we do is basically we're comparing ZX, ZY for your test data. So for the test data, basically you put a thermal imagery here, you get a ZY. For the gallery images, you only have all their ZX, and you just compare Euclidean distance. And if you do that for the fully connected, you can see for the thermal imagery, the rank 1 is 60%. For the mid-wave IR on another data set, the rank is 92. Okay? And the size of the database, it becomes, in a minute, I'm going to show that too. Now, when we get rid of the fully connected, that's very interesting. We basically reducing the number of weights a lot. And what's going to happen by using just a global pooling? And you notice that the performance actually goes up for the thermal from 60 to 67. And for the mid-wave IR also goes up. And I think the only reason is basically we just reducing the number of weights because we don't have enough training data sets. We compared the performance of these the new algorithms with our previous work. There's not a lot of algorithms in this arena. Most of it is from ARL. And actually, I'm comparing this not with, I think, yeah, with Ben, who's sitting here. He also used couple MLP. In this example, I'm using couple CNN. The reason we used couple MLP in the beginning was because we didn't have enough training data. We thought we cannot actually implement this. So of course, I jumped. I didn't go into details. But what happened is we are not sending the whole face to the CNN. We only use 40 by 40 regions. Okay. So because there's not enough training to do the process. So we basically have 40 by 40 pixels overlapping windows, and we process them independently. Of course, you can, when you do convolution, you can do convolution all the way until you basically get fully connected. So you can actually do this by a whole image also. But with processing is, when I'm matching, I'm only matching 40 by 40 of overlapping blocks, and we average all those results. So that's a little bit detail. So going to the comparison, so you can see that our convolutional neural network, we use couple convolutional neural network, you can see that the performance is better than our previous approaches. So we have come up along quite a bit. We use also couple dictionary sparsity, and one of my ex-students was doing that. And basically you can see the performance we have pushed up the performance in last 4 or 5 years. Now, as Sean said, at ARL, because of the thermal imagery, all the details in the image face has washed away. We also exploited using polarimetric thermal information. And one of the things we did in this work, and this shows the database. So you can see this is the thermal imagery. This is the thermal imagery, and this is the polarization state images. And you can see that the polarization state images have some surface characteristics. And the goal here is to input all these 3 imagery into our algorithm and compare it with the thermal, which means only this one, and do we do better or not? And we're going to show you that, yes, we do better because the polarimetric state information basically gives you the surface topography of the faces. So you have the same algorithm basically, except that now my thermal CNN in the input is not just the thermal image, also we have the polarization state information. So the input will be just like RGB, will be basically S node, which gives you the thermal imagery. S1 and S2 give you the thermal polarimetric state information. And we do the same thing. Of course, these some engineering tricks are going here. We pre-train these things on ImageNet, then Casio faces, lots of things going on before I actually try to, and then we take the visible imagery weights, we transfer it here because we don't have a lot of thermal, and we train these on Casio thermal imagery and so on, and then after that we train it on our training data sets, because our training data set is not so big. So there's a lot of engineering going on before we start. So again, the same thing. Again, we don't do the whole image. We don't have enough training data. We do on blocks of 40 by 40 overlapping images. And the goal here, again, is the same thing. Given the visible imagery, you get a Z1. With the thermal and the polarimetric information, you get a Z2. The goal of the contrastive loss is to force these two to be as close as possible. And there are lots of ways you can do besides contrastive loss. You can do triplet loss, you can do central loss, or combination of these, and people have done that in computer vision arena. So let's look at the results. When we input thermal, the solid lines are thermal. And the dotted lines are the solid lines are thermal with polarimetric. The dotted lines are purely thermal using different algorithms. So when we're using our approach, the coupled CNN using thermal and polarimetric, basically you will get quite a good result somewhere here. These are the rank basically. And previous result, most of them from ARL, I think this work is from Sean. And you can see that original work that Sean did long time ago, basically that's where we were working. This is now what you can see that within 4 or 5 years we basically have pushed this all the way up here. And this, the red one, is basically the algorithm I just showed you in the previous page. Now, going back to same, since we've been working this, we said, well, can we use the same coupled deep neural network for other heterogeneous problems? A sketch versus visible imagery. And we have actually done this, plus many other things, and same idea, and basically develop a coupled neural network, one dedicated for sketch images, and one dedicated for for visible imagery. And can we basically match them together? Using the same idea again, using contrastive loss to match this. So you have a thermal image, and basically you have a gallery of suspects, and you want to say basically this sketch, which one of these suspects basically matches. And obviously you already have trained your sketch CNN, and as well as visible imagery CNN, and you have coupled them through the contrastive loss. And basically you're given a sketch, you find a Z1 and you match it Euclidean distance-wise, which one of Z2 of any one of these guys matches. If it matches, then that's your visible imagery or your suspect. And if you look at the results on the database that we have, again, training data is very limited. You have to basically do a lot of engineering things before you make this work. So you can see that the ranking in this case, rank 1, is quite high. WACV18 on the database that we have performed. Now let me shift the heterogeneous problem into completely different, which is, I think this is something we recently have worked and is very interesting. Now, what is the goal here? The goal here is that given facial attributes of an individual, so we have the facial attributes of a suspect. For example, it's the suspect is curly hair, blonde, young, female, pointed nose, all the facial attributes that the victim can describe. Given these facial attributes, can we quickly go through our largest scale visible gallery and bring up all the images that matches these facial attributes? And we want to do this extremely fast, okay? So how can we do that? So basically, you have your features, facial features only here, okay? Not soft biometrics, but the facial features. And we basically have our facial features here that the suspect has described, and we input that to an MLP, and we basically get an output. And then you have faces of all these people in our gallery also. So we basically also have a CNN. It gives you an output. But here, there is a little bit of problems, and the goal is that the output of these two neural networks, we want it to be binary, because we want to do the search very fast. This comes under the literature on hashing, and we call this deep hashing. So what we want to do is, basically it's a kind of clustering of my database. I want to cluster my database based on attributes. So people who have similar attributes, we cluster all their images into one cluster, and that's the goal, okay? Now, so what we want to do is, we want basically put the attributes here, we get the binary output, we want to force the output of this neural network to be binary, and then people who have the similar or same attributes, we want their output of their CNN to be exactly the same binary code, okay? And we call hash codes, okay? So if I can achieve this, then if somebody describes an attribute, I have the attribute, a binary output. I'm going to match it with basically my gallery, which I'll represent it in a binary format, because I have the binary version here, and we just do a one-to-one binary search. And if the Hamming distance is close, I display that, okay? Everybody follow? Okay, now this is very useful for law enforcement, because you have a victim just comes and describes what happened, and basically in a second I can tell you from the huge gallery of suspects, and I can tell you these are possible suspects. And this is useful for virtual police lineup. In the case of lineup, basically the guy comes, describes the person, and they go look at the pages of suspects, and they go even into the street, find dummies to line up the people. So this will actually help us very quickly. We can extract and bring lots of pictures of suspects, and the victim can identify if any of those resembles the person who committed the crime. So let's do an example. Does this idea works? So what we're going to do is, we're using this database, the Celebrity A database, which is huge with 40 attributes. And we input, like for example, we input these kind of attributes. And the remaining attributes that doesn't exist or the victim doesn't know, we basically we put 0 as null. And when we retrieve, you can see retrieving these guys. Okay, and really chubby face, for example, hat and so on, it does to some extent works. And if you look at another set of imagery, again we input these as input to our soft biometrics or facial attributes, and you can see that does extract the information that the facial attribute represents. At least the first few ranks do represent the face that we are basically interested in. Now remember, the problem is a little bit different from the coupled neural network. I'm not discussing the technical part. Remember, we're forcing the output here to be binary. Without going into technical part, that itself is not easy. Because if you use ReLU or if you use softmax, okay, the output is not binary. Here I'm forcing the output to be binary, okay? And there is a little bit of technical issues there, and there are lots of papers how to solve that problem. Now, how much more? Very good. So what happened is, if you remember, this we did a while ago, identical twins. We have a lot of data of these identical twins. How can we distinguish between two identical twins? And this is very important for companies who develop face recognition systems. If they can distinguish identical twins, their algorithm should work very well. So what we did was, can you identify these two if they are genuine pairs, same ID, or these two are identical twins, but they're not the same ID. It's very difficult even for the humans. Can you develop an algorithm or a face recognition system that can do that for you? And basically, this is very similar to work that has been done previously using Siamese convolutional neural networks. And Siamese network is not new again. It has been used for many other applications, such as signature recognition of genuine signature or imposter genuine, and also for dimensionality reduction and so on, and also metric learning. But we use the same idea, same approach for this distinguishing between identical twins. And if you basically, what we do, again, we're training that coupled deep neural network. We input to the neural network genuine pairs, identical twins which are same ID, and imposter pairs. And basically running the coupled CNN that we did previously. And let me show you the results. If basically this one shows the difference between the identical twins, okay, the Euclidean distance between the identical twins. And you can see the red one is basically, the blue one is basically the genuine pairs, the red ones is imposter. So you can see that the difference between identical twins, very difficult to distinguish. They overlap so much, as you can see. So what is the goal of the coupled deep neural network? The goal is to force the red one to go up and the blue one to go down, okay? And if you look at the output of our coupled convolutional neural network, basically, still we have a problem because it's very difficult. So some of my red points now pushed up, some of my blue points has been pushed down. I'm trying to distinguish between the red ones and the blue ones. I want the red ones to go up, the blue ones go up, and it's still not quite doing the job. So this is the original without processing, okay, without going into the output of the convolutional neural network, that means without going into the embedded domain. Basically, that's what you get in the original domain. Everything overlaps. In the output of the convolutional neural networks, the coupled convolutional, when we compare the output, basically that's what happens. There's still a lot of overlapping. And basically, this shows the ROC curves, what's happening. So there's a lot of work still to be done for distinguish between the identical twins. And that's my last chart. Any questions?
All right, anybody have any questions?
I want to know how big is the database of twins that you have?
Oh, that's a huge database. So we have been collecting data since 2009. Every year we go to the Twins, what's the Twins Town, right? So we go to the festival. There's a festival that in Ohio, Twins Town, and we collect data. And it's very exciting. We collect actually this data set. We have the faces, voice, and fingerprints. I only work on the faces because it's more challenging because fingerprints of twins are different. So we have a lot of data to process. And nice thing about it is we have 2009, 2010, 11, so many years. So you can even see the age progression.
So when you're looking at attributes, having done a lot myself, right, one of the things we found was that binary
binarization of the attributes for a small data set is okay, but when you get to millions of people, binarization of attributes doesn't give you a very good lookup function, especially if your attributes are even slightly noisy. The closest people in terms of the binary attributes won't be very good matches. So I don't quite understand why you're trying to make it, and speed-wise, the difference between binaryizing it through the network and then using quantized lookups, which is a different technique, on most computers makes almost no difference in speed. So,
Even on a large database, if you have a huge...
Well, so I don't know what you consider large, but like 7 million is the large. But at 7 million, binary attributes don't provide a very good index.
Right. So what happened is, as you said, depending on the database, yes, if you binarize the attributes, obviously you lose information. That's one of the problems that this. So going back to the convolutional network and MLP, the error or distortion caused by the binarization, I try to learn it by network. So that's one of the things is this algorithm is doing. When you binarize something from variable values, obviously as Terry is saying, it's correct, you're going to lose the performance first of all. So one thing is binarization, you lose performance. The other thing is computationally what happens. So because we lose performance, we try to learn the performance by adjusting the weights because I force the output to be a binary. So that's one of the advantages. I'm not losing performance as much as I would if I just take the output of my neural network and just quantize it, binarize it. That's a bad thing to do. You're not going to basically do performance-wise, you're going to do poorly, okay? Now, computationally, I think Terry's correct. If your database is not huge, okay, especially computers becoming faster and faster, so if the database is not huge, yeah, obviously you don't want to binarize. Just match the output of the neural network, right? Basic that to do that. What was your other question now?
My comment was that, so that if the database is large, using attributes, even if you just try and match numerically, is not a very good way of looking up. We had a paper in CDBR 2012 that if you really want to match multiple attributes at the same time, you have to do a very sophisticated comparison analysis. We use extreme value theory to do it, right? But otherwise, you don't get good matches on a large database. Small database, it's okay, but the distinguishing characteristics of how far is close varies by attribute and by person within those attributes. So a simple lookup is not a very good way in a large database.
Yeah, but that depends the number of attributes you base, more attributes, as I'm showing here, is basically this is the output of the neural network. So if your attribute, you just put female, it would match all your 7 million, or half of your 7 million images, that's obvious. So it depends on the number of attributes. So what happened is also the rank, how far rank do you go down? So what happened is there is still a merit, because if I use the attributes, reduce my gallery from 7 million even to 1 million, and then use some clever computer vision algorithms to exploit this, right? To basically, maybe what I can do is, which actually we are doing, that's his paper next, what happened is combine the sketch with the facial attributes. So there's lots of things you could do. You could do simple engineering, reduce your gallery using this. So basically my rank, I will bring up the first 1,000 people in my gallery, and then I use the sketch to match the first 1,000 against the first 1,000. Of course, he doesn't do that. He does more clever. He combines the facial attributes and the sketch jointly, rather than, like engineering work which I'm explaining. So there is merit, but you're absolutely correct. So basically, if your attributes, you have only 3 attributes, male, and basically brown hair, and a couple of other things which are very common in half of the your gallery, you will basically bring up the whole gallery. So it depends on how much attributes you're inputting, especially on a large database. Absolutely correct.
All right, I think that's probably all the time we have. Let's thank Professor Nasrabadi.